Okay, so this video is about the topic of hybridization. So if you stop for a moment and you think about the model of electrons that we talked about during the atomic structure topic, then you could think about something like carbon, and you would think of carbon as having a configuration of 1s2, 2s2, 2p2. And so if we drew out its orbital diagram, we would get something like this. And if we thought about the orientation of those orbitals, we would remember that we have s orbitals, which are spherical, and then we have p orbitals, which are all at 90 degrees from one another. We have the x-axis, we've got a z-axis, we've got a y-axis, right? So that's what we covered in the atomic structure unit. We have certain shapes of orbitals, certain angles that they exist at, and we have our atomic orbitals, our configurations, and our box and arrow diagrams. Now, we then go into covalent bonding, and we start to completely ignore that, more or less, and we start to look at carbon like this. And we just draw carbon with 4 dots for 4 unpaired electrons, and we know that carbon makes 4 bonds, and so we often see carbon forming 4 bonds. But when you draw just its dot structure, you have carbon with 4 dots. And then we learn the VSEPR theory, the valence shell electron pair repulsion theory, and we tell ourselves, okay, well, if carbon forms 4 bonds, like if it forms methane, then the shape it's going to have, because there are 4 electron domains, is actually something that we call tetrahedral. So it has this sort of 3-dimensional nature to it, and all the bonds are 109.5 from one another. So if we take a moment and we pause and we think about these two things that we've sort of accepted at this point, hopefully we see that there's some contradictions between them. On the left, in Unit 1, or whenever we cover this, when we do atomic structure, if you look at carbon's electron configuration, it actually, according to what we studied in that unit, it only has 2 unpaired electrons. Well, in this unit, or in the covalent bonding unit, we draw carbon with 4 unpaired electrons. So that's one contradiction. The second contradiction is that those electrons that are unpaired should be at 90 degrees from one another because they're p orbitals. So maybe they're in this orbital and maybe they're in this orbital. So we've got like some kind of 90-degree orientation issue happening. But when we learn the shapes, we learn that if there are 4 electron domains, that those electron domains are going to spread out evenly, and we end up with a 109.5 bond angle. So we have a few different conflicting ideas here. We have issues about how many unpaired electrons carbon has, and about where those bonds should be allowed to exist. And so the main point in looking at this is that clearly we need some theory, some idea that can bridge the gap between these two theories. And so the good news is we're still going to follow the atomic orbital theory when we talk about atoms. We're going to use our electron configurations, 1s2, 2s2, 2p2. We're going to draw s and p orbitals the same way. So all of that is still fine when we talk about atoms. And the VSEPR theory is still going to be totally fine when we look at molecules and when we draw them and try to figure out their geometries. We just need a theory that can explain how we get between one and the other. And that theory is hybridization. A little bit like when you look at sigma and pi bonding, and this idea that orbitals can mix together, right? So we said when an s orbital combines with an s orbital, we get a bigger orbital that we call a sigma orbital, right? So that was an s and that was an s, and then they overlap and we get this sigma orbital. And we said that's possible because, well, s orbitals are really just waves. They are wave functions of electrons, and we're allowed to add waves together to get new wave functions, constructive and destructive interference when we add together waves. So the idea is somewhat the same here. The idea is that when things bond, atomic orbitals, meaning s and p orbitals, are able to mix together and create new orbitals when things are bonding. And these orbitals are a mix of s and p, and therefore they are hybrids. They are hybrid orbitals that have some of the characteristics of an s orbital and some of the characteristics of a p orbital. Now, this is the hybridization process as it's normally described, and it's done for carbon. So we have the 1s2, 2s2, and the 2p2 shown here on the left-hand side. That's the starting configuration of carbon. And the idea is when the bonding process is happening, when atoms are colliding and there's some energy present from the collisions of these atoms, the electron in the 2s can be promoted to the 2p. And so now that gives us our 4 unpaired electrons that we associate with carbon when it's bonding, that it typically forms 4 bonds. And then the s orbitals and the p orbitals can mix together to create up to 4 even orbitals. And these orbitals here, you can see, are shown having all the same energy. So these are the hybrid orbitals. Now this is how they're represented with the box and arrow diagram. It's just to get a sense of their relative energy and how the electrons would be unpaired. This explanation is generally not required of you, the electron promotion and then the orbitals mixing. But I suppose it is possible that they could ask something about that, and you would just say, that's all you'd really have to say. When orbitals hybridize, first an s orbital is promoted to the p level, and then the s and p orbitals mix together to create hybrid orbitals. Now, they're called sp3 orbitals in this particular example because one of these s orbitals, one s box, combined with all 3 p orbitals to make 4 new orbitals. So notice that the same number of orbitals that we use, so 1s plus 3p, that equals 4, we still have 4 orbitals afterwards, and now they're all equal. And so we name this type of hybridization sp3. So it just describes which orbitals went into making them, 1 s orbital and 3 p orbitals. Now, if we have 4 equal orbitals, we end up fixing both of the issues that we had on the previous page. Having 4 equal orbitals gives us 4 unpaired electrons because the electrons naturally are going to spread themselves out to the empty orbitals before pairing up. It also now allows, if we have 4 even orbitals, they're even in energy, then 4 even orbitals will push each other apart as far as possible, evenly. And that gives us the 109.5 bond angle. That gives us the tetrahedral shape. Because they're all even, they'll spread out evenly, and we end up with the tetrahedral orientation. And so it's essentially saying that if we took this s orbital and these 3 p orbitals and we mixed them, we would get something that looked like this. We would get 4 sp3 orbitals that were all even in size, shape, and energy, and they point out from each other in a tetrahedral arrangement. And so this idea of hybridization is bridging the gap between an atomic model that didn't really align with a molecular model that we had. Now, that all sounds incredibly complicated, right? It really seems like a lot, but actually what you get asked to do on the IB exam is fairly straightforward. The most common thing that you get asked to do is to identify the type of hybridization that exists in something. And really all you have to do is learn to associate a type of hybridization with an electron domain geometry. So we have essentially 3 electron domain geometries to worry about. These are the SL electron domain geometries. We have for 2, 3, and 4 electron domains, we have the shapes linear and trigonal planar and tetrahedral. And so when we introduced those shapes, we said, well, 2, that's as far apart as 2 electron domains can push or repel. Trigonal planar is 120 apart. That's as far as 3 equal electron domains can repel, and tetrahedral is for 4. And so with these different different geometries, they each have an associated type of hybrid orbital that aligns with this shape. And so for tetrahedral, we saw the type of hybridization was called sp3. That when you combine an s plus 3 p's, you get 4 new orbitals out, and you get 4 equal orbitals out. If we only need 3 domains, then we're going to combine an s with 2 different p orbitals, and that will give us 3 domains, and we'll call those hybrid orbitals sp2 hybridized, or sp2 hybrid orbitals. And when we only need 2 equal domains, we'll say that s and 1 p orbital combine, and that creates 2 sp orbitals. So the hybridization types are sp, sp2, and sp3. And it's simply, you just have to learn to associate them with each one of these shapes for electron domains. So 2 electron domains is always going to be sp3, 3 electron domains will always be sp2, and 4 electron domains will always be sp3. You might be wondering, okay, well, if we use 2 of the p orbitals, where is the other p orbital? The other p orbital is remaining behind as a normal p orbital. We would call it an unhybridized p orbital. And in the sp hybridization, because we only use 1 p orbital in the hybrid orbitals, that means there's 2 unhybridized p orbitals that are left behind. Okay, so let's put this into practice and see what we can figure out. Okay, so this is an example here where, let's see, BeH2, if we drew it, let's see if what I said holds true. So we've drawn BeH2, it's one of our weird incomplete octet examples, and I can see that there are 2 electron domains. As soon as I know there are 2 electron domains, I'm going to associate that with a linear geometry, but also with an sp hybridization type. That's it. That's how you figure out the hybridization type. If there are 2 sp, there's only 2 orbitals mixed together to make the sp orbitals, and the sp orbitals end up taking a linear orientation, which aligns with what we would have said the geometry was here. With BH3 or BF3, another incomplete octet example. So we draw this out and I get 3 bonds, 3 electron domains. And as soon as I know that there are 3 electron domains, I'm going to associate that with sp2, 1 s orbital and 2 p orbitals, 3 orbitals that are all equal will be called sp2 orbitals. And 3 even orbitals will spread out in a trigonal planar shape. So these are what sp2 orbitals look like. Okay, and then this page here is just to remind you about what I just said, that as soon as you know there are 4 electron domains, you know it's sp3, 3 electron domains is sp2, and 2 electron domains is sp. We're also going to see that this aligns with some other things that we've seen, like the sigma and pi bonds and how we can get the correct orientations. So a common one that we look at first is CO2. So if we draw the Lewis structure of CO2, we should get something like this. And we would say there are 2 electron domains, and we would say it was linear. So check, bond angle 180. We also would have said that there are 2 sigma and 2 pi bonds in this molecule. There's 2 double bonds, so the extra bonds are pi bonds, while the single bonds are the first, or one of each bond has to be a sigma bond. So we've got those things covered, and now we have to add into it one more thing, which is hybridization. Well, as soon as I know there's 2 electron domains, I'm going to say it's sp hybridization around the carbon atom. So kind of like VSEPR theory, hybridization, you use it to identify the hybridization around one atom at a time. So the carbon atom has 2 different electron domains, and that's why I would say the carbon is sp hybridized. I would have to give a different answer for the oxygens in this example. I'd have to consider them separately. If we want to, we could do it quickly. The oxygens have 1, 2, 3 domains, and so the oxygens are actually sp2 hybridized, both of them. since they both have 3 electron domains. So the carbon is sp hybridized and the oxygens are sp2 hybridized. Now we're going to do one more of these cartoon bubbly drawings to try to illustrate this all. This is not something you have to do, but just to try to make it all tie together. So I've got these carbon atoms, and I said they're sp hybridized. So sp orbitals take a linear orientation because they are even. So that's an sp, and that's an sp. And then I've got these oxygen atoms, which we said are sp2. That's kind of like in a trigonal shape, okay? So we knew that there were 2 sigma bonds. Well, the sigma bonds are happening in this example because we know sigma bonds can happen between any kinds of orbitals. There's axial or head-on overlap happening between this sp2 orbital and this sp orbital. And then the same thing on the other side, this sp and this sp2. So there's one of the bonds between the carbon and oxygen is from that head-on overlap. Okay, well, what's going on in these other sp2 orbitals? Well, that's where the lone pairs are. So hybrid orbitals can exist where you have bonds, but they can also be where lone pairs are. So it allows the lone pairs to spread out away from the bonding pairs. Okay, well, what about the extra bonds? What about the pi bonds? Well, we already know that pi bonds happen between parallel p orbitals. Since this carbon in the middle is sp, it has 2 p orbitals left over. It has one that's straight up and down, and it has another that's sticking in and out of the carbon at 90 degrees. So by being sp hybridized, there are still 2 p orbitals left over to form those 2 pi bonds. This oxygen is sp2, so it still has 1 p orbital left over. And that's all it needs. So it can form the extra bond here. So we get a pi bond there. And in this one, that oxygen is sp2, so it also has 1 extra unhybridized p orbital. And I get a pi bond over here. So when we actually start to draw these hybrid orbitals out, the hybrid orbitals end up being involved in sigma bonds, and they end up being places where lone pairs are located. And then the extra bonds, the pi bonds, are always still made from p orbitals that are left over. So when we have sp3 hybridization, we're not going to see any pi bonds. Because in sp3, there's no p orbitals left to do the pi bonding. When something is sp2 hybridized, there's 1 p orbital left. So like these oxygens, an sp2 atom will often end up with 1 pi bond because it has 1 p orbital. When atoms are sp, they have 2 p orbitals left that aren't in the hybrid orbitals, and so they will often be involved in 2 pi bonds. So with hybridization, the most important skill is that you can draw something and recognize the type of hybridization that it has, and we do that simply by looking at the number of electron domains. That's the quick way. Then in a more complex way, we can think about the hybridization on multiple atoms. We can think about which ones are involved in the sigma bonds and holding the lone pairs, and then what the p orbitals that are left over that are responsible for the pi bonds.